Hey everybody, and welcome to our lesson on not factoring by grouping. Our lesson is actually on this blue sheet. It's called Using Exponential Growth and Decay Models. And in our online book, it's section 8.3. But in order to introduce this lesson, I do want to review factoring by grouping because there's this little part of developing the formula where factoring by grouping is required, and I find that if we go over it sooner than later, it's easier to understand in the lesson. So I just have a little example here, and you don't even necessarily have to write this down. You can just sort of understand. So say I wanted you to factor this polynomial. So you've got 3 times the quantity x plus 2 plus 6x times the quantity x plus 2. And the reason this is a great candidate for factoring by grouping is that on either side of this plus sign, you have terms that each have a component that is similar. So if you look on this side here, just looking on this side of the plus sign, we've got an x plus 2. And then if you look on this side, we also have an x plus 2. So we can essentially factor out that common x plus 2. So it'll kind of look like this, x plus 2. And then you're left with a 3. And then this plus sign drops down, this green plus sign, and then a 6x. So this is considered the factored version of this polynomial. Now, you could always check it. I mean, if you check your work, one way to check it would be just to go ahead and distribute the 3 through this quantity. So if you distributed the 3, it would be 3x plus 6, and then plus, and this would give us 6x squared plus 12x. And so if you combined your like terms here, you would have a 6x squared and a 15x, and then your lone 6 here. Now, to show that this is also correct, my factored version, I could just take my x and multiply it to the 3. So there's 3x. And then I take the x and multiply it to the 6x, so 6x squared. And then 2 to the 3 gives me a 6. And 2 to the 6x gives me a 12x. So we also have 6x squared, and then the 12x and the 3x make 15x, and then 6. So they're matching, so I have factored correctly. Now, how's this going to come into play today? Well, today, during the lesson, we're going to be faced with a problem that looks like this, which I know is kind of strange. It'll make sense in a minute. But here's what we've got. We've got P times the quantity of 1 minus R minus R times the quantity of P times 1 minus R. So if I kind of use my same strategy here, let me highlight the minus here that separates these two terms. So I'll put a circle around here and a circle around here. Now we need to see if it's a candidate for factoring by grouping. Do they have any similarities? Well, they sure do. The P times the 1 minus R here matches the P times the 1 minus R here. And so the common factor is P times 1 minus R. So I'm going to go ahead and pull that out to the front. So it's going to be P quantity 1 minus R. That'll be in the front. Now, what am I left with? Well, in this term, I have nothing left. I mean, P times 1 minus R is already out here. So when you take the entire factor out, you're just left with a 1. Then you bring down your minus, and all that's left here would be this R. So this would be the factored version. P times 1 minus R times 1 minus R, which in our notes today, we're going to write as P times the quantity 1 minus r squared. See, because 1 minus r times 1 minus r gives me 1 minus r squared. Okay, and let's do one more. Let's do one more of these. Suppose you were to take this problem and factor by grouping. Okay, so again, let me highlight this minus. Let me circle this side of the minus and this side of the minus. So it's a candidate for factoring by grouping because this guy right here matches this guy right here. And so the common factor is p times 1 minus r, quantity squared. Then I situate my second quantity with the leftovers. So from this term, I have nothing left, so I just say 1. Again, because if I take my outside here times 1, I'm right back to this. Bring down the minus, and here I'm just left with the r. And so my final answer will be p times 1 minus r to the third. 1 minus r to the second times 1 minus r essentially to the first. We add those exponents, and now we have 3 1 minus r's. Okay, so that's just a little precursor to the lesson, and I think that's going to make things a lot easier in just a moment. Okay, so let's turn to the blue sheet now. Okay, so it says, if you just open up right here, it says you buy a new car for $35,000. But now the value of the car decreases by 12% with each passing year. So the value of the car is on the decline. The question is, what will the value of the car be in 5 years? So what I'd like you to do is pause this video and try to find it. Do it any way you like. I even said this on my original notes here. Let me cover up this answer. Students may solve any way they choose. So go ahead, pause the video, come back when you're done with a final answer, and I will give you the final answer. Okay? Okay, so hopefully you paused and you worked stuff out. Here is the final answer. Are you ready? It's $18,470.62. Did you get that? If you did, you know how to work with money. Okay, I'm going to take you through what I did in this little chart that follows, and you can see that final answer is right here at the bottom, but I'm going to take you on a systematic step-by-step process of how I got that. So let's check it out. What I did is I made a table. I put the time in years down this column, and then the car's value down this column. So here are my computations. When the car was first bought, I would say no time has passed. You drive it off the lot, it was worth $35,000. But now what happened was a year has gone by, and so my $35,000 now gets subtracted, or something gets subtracted from my $35,000. Well, what? Well, 12%, which is 12 out of 100, or 0.12, times the car's value. So 12% of the original value gets deducted from the original value, and you're now sitting at a car worth $30,800 after the first year. Look how much it's depreciated just in 1 year alone. That's 12%. And then you just go on. Next year, now this is your starting value, $30,800. We're going to take away 12% of that to give us car's value after 2 years. And this process just continues. 3 years, you take this $27,104, subtract 12% of $27,104, and you're here at $23,851.52, and then it just goes on. And you end up, after the 5th year, with a car that's worth $18,470.62. Okay, so what we're going to try to do here is develop a formula that's going to do problems like this for us faster, because this is time consuming. So in this chapter where we're studying exponential growth and decay, we're going to be developing a formula. So what we do when we develop a formula is we take the specific and we generalize it. So let's see if we can generalize this. It says in general. Okay, the time in years is staying the same. Time is consistent. It's always going to be 1 year, 2 year, etc. But the car's value, I want to be able to do any car, like maybe not just the $35,000 car, maybe I want to do a $20,000 car or a $10,000 car. So I want to make the right side of my table really general. So in math, in this unit, we call the car's initial or starting value P, principal, okay? And if you look down here a little bit later, you can see that P stands for the initial or starting amount. So our P right now represents 35,000 or any starting value that this would be worth. Now let's see what we do. Well, in the real life example, we took the P and we subtracted the percent, 12% of P. Now in this unit, the percentage rate we call rate. So the 0.12 is the percentage, the rate at which we're depreciating. And you can see this down here, R is for rate. So we took, after 1 year, we took the initial amount, P, and we subtracted the rate times that principal. Okay, that's what we did right here, 35,000 minus 0.12 times 35,000. Now look what I did mathematically here. I factored out a GCF, I factored out a P, and I'm left with the quantity 1 minus R. So this is factoring by the GCF. So I went from P, after 1 year, I'm left with P times 1 minus R. So what do I do then? Well, I took the 30,800, I brought it down. So I'm going to take the P times 1 minus R, I'm going to bring it down. So this right here is looking like the 30,800. These match, just like these two matched. And now I'm going to subtract the rate times that same value. Now, didn't we already do this? Didn't we already take P times 1 minus R times P times 1 minus R? Didn't we already factor that earlier into P times 1 minus R squared? So that is what I have right here. We did factoring by grouping and got this. Then we take this guy, bring him down. P times 1 minus R squared minus the rate times P times 1 minus R squared. And didn't we factor that? Where is that? I have it somewhere here, right here. We took P times 1 minus R squared minus the rate times P times 1 minus R squared, and it gave us P times 1 minus R cubed, which I have right here. And this just continues. And you can see it in the next two lines if you're really understanding this. What happens is you start to see a pattern. See this formula evolving? So you started with P. You moved to P times 1 minus R to the first. P times 1 minus R to the second. P times 1 minus R to the third. P times 1 minus R to the fourth. P times 1 minus R to the fifth. And are you noticing that the year over here matches the exponent? 4, 4, 3, 3. See, that's your time in years. Your exponent is your time. And A is just going to represent your final answer. A is going to represent this final answer. So, check this out. When a real life quantity decreases by a percentage over time, the final amount can be modeled by this equation. A equals P times 1 minus R raised to the T power. And I'm getting that right off of here. Now watch how much easier this is. So if you had had this formula, up here, when I presented this first question to you, you wouldn't have had to do all this work right here. You would have known that A equals P times 1 minus R to the T. You would know that A represents your answer or your final amount, the car's worth. P was the original principal, the starting amount, that was $35,000, times the quantity, 1 minus, your rate was 12%, and you wanted to know the value after 5 years. So you would have grabbed your calculator, which I can't find mine right now, so, oh, here it is. You would have plugged that into your calculator, and you would have gotten 35,000 times 1 minus 0.12 raised to the 5th power. Check it out. There it is. 18,470.62. 18,470.62. Look at the difference. By developing that formula, we don't have to go through all this tedious work anymore. Okay, check it out. So turn it over. We're almost done. Now, there's also growth. Now, this was a decline. This was a car depreciating. So you can see that we have a minus sign there with our rate. What happens if we grow? Well, when a real life quantity increases by a percentage over time, because some things grow in appreciation, the final amount can be modeled by, it's the exact same equation, just with a plus. And that's just because if something was growing, we would have changed all of these to pluses, which would have changed all these to pluses. Okay? So let's read this. The population of Coleman, Texas grows at a rate of 2% annually. So there's R. R is 0.02 or 2 over 100. If the population was 5,981 in the year 2000, so I'm thinking that's my P, my initial, 5,981. What was the population? So what's A? What's the final amount? In the year 2010, so T would be 10 because from 2000 to 2010, that's 10 years. So I've got my rate, my initial pop. I want my final at year 10. So I plug it in. Now we're growing, so we're going to use the plus. So A equals 5,981 times quantity, 1 plus my rate, 0.02, raised to the 10th power. And if I put that in my calculator, I get, let's see what I get, 5,981 times 1 plus 0.02 raised to the 10th. 7,290, and it says round up to the nearest person. So I'm going to go with 7,291 as my population 10 years later. All right, last example. Tommy bought a truck 7 years ago that is now worth $12,348. That's interesting. So we don't have the initial amount. We have the amount 7 years in. So I am actually given A. So at 7 years, the amount is this. I don't know the original amount. I do know the rate, 14% or 0.14. Okay, so Tommy bought a truck 7 years ago that is now worth $12,348. If the value of the truck decreased 14% each year, how much did Tommy spend on the truck originally? Round to the nearest dollar. Okay, so now we're depreciating, so I want to use this formula, right? And so for A, I'm going to plug in 12,348. I messed up. Let me do that again. 12,348 equals P times 1 minus, what's my rate? 0.14, raised to the 7th power. So to solve for P, all I have to do is divide both sides by this guy, 1 minus 0.14 to the 7. And I will have solved for P. So P equals, I'll do alpha y equals fraction 12,348 over quantity 1 minus my rate raised to the 7th year, enter. It looks like the truck was originally worth $35,490. Okay, so that is the lesson. Now, I threw a lot at you, especially this part right here. Okay, this part right here. But really what I need you to take away from this lesson, is this. Really, your two takeaways are, when you grow a quantity at a certain rate, your formula is this. You just have to memorize it. You have to know what this is, what this is, what the R is, and what the T is, and we talked about all that. But when you're depreciating, you're losing worth, so appreciating, depreciating, you just change one sign, and it's A equals P times 1 minus R to the T. So these are your takeaways. I just didn't want you to think these formulas just poof came out of nowhere. I wanted to derive them, and that's what we did there. Okay, thanks for watching.